So one thing is that I try to put homework to within this weekend. Okay. And then, all right, so we have talked basically mainly about like the cut matching game in these 3 lectures. And is there actually any question you want to ask regarding this? Okay, so then so the cut matching game that we have seen so far is that what we will get is just an expander, right? Such that each node, like the max degree, is at most the number of rounds. Which is something like log n or log square n. Okay. So first of all, actually, can we make sure that it's not just the max degree, but you get that every node has the same degree, uniform degree. So how to make sure of that? Like you want that, okay, everyone, let's say everyone has degree of log square, not just like between 1 to log square. Yeah. How can we do that? That is true, actually. Yeah, you can, like in each round, when you choose a cut A and B, okay, you have, you add a matching, but the guys that you don't add, you just kind of cheating by adding self-loop. That's good too. Another way to just make sure of this is that, suppose that you find a cut A, then what we can do is that, so first of all, okay, what we can do is that, what if we find like, we just return some cut that contains A, and it has, it really a bisection, so it really separates the graph into two halves. And if that happens, then the matching player have no choice but to add perfect matching, right? And everyone will get will increase its own degree by 1. And actually, this is something that happened in the randomized algorithm, right? In the randomized algorithm, we really return bisection, a median cut, but you can actually see is that even in the deterministic algorithm that we have seen, although I said that we just, like the cut player just need to return a cut that which is balanced and sparse, it's fine to, if we just, once we find this cut, we just return something that contains this cut. So we can look at the analysis for the right, where is it? Yeah. So just to recall, here, like in every round before the last round, we just say we return the balance path cut. Now I claim that just once you find this, just return instead of return this, then return let's say this where they are completely balanced and this one does not cross that does not cross. By doesn't cross, I mean, I mean like one side, A prime kind of contains A. Yeah. And why this is fine? Well, we can really just look into this analysis, and you can verify that like even if you use A prime I and B prime I, this is fine too. And why is that? Because all we really need is that so okay. So what we have shown, like all we really need is that even if we if we return A prime I, right, then the matching here, like the matching player still need to add some matching, and the matching that the matching player add now is just a bit more restrictive. Instead of saying that anything, just look at any node inside A, right? Now instead of we know that any node inside A will be matched to someone outside A, we know that now it will be matched to someone even outside A prime. So like really the same proof just work. Yeah. Yeah. So that's the idea. Like each node A. So if we use A prime I instead, like A prime I and B prime I, each node A in A must be matched to some node B even outside A prime, not just outside A. So we kind of see before that if each node in A is matched to some guy outside A, then that's like something could happen. Now it's even more like kind of better for us. Yeah. So which means that we can really force, like just by returning a bisection instead of just some balance cut, we can really force that you will get a uniform degree expander. But okay, and by uniform degree is either like it's really the number of rounds. That's the degree. Now, okay, what if we want an expander which is that have degree like profile something that we want? not just uniform degree. Okay. So there will be like a way to cheat this as well. Basically, so suppose that you have built, like, suppose that what you want is an expander where one node have degree 10, let's say, or like, so, okay. Let's say this is a number of round, call it R, and let's say that the degree profile that we want is like some, is like, yeah, like each node is like has degree which is a multiple of R. Okay, suppose that we want this. So what if we want one node to have degree 10 R and every other node we just want degree R? Then we can build this too. And the reason is that it's kind of cheating. Like we just really start by saying that we start with just do a normal cut matching game. And once we are done, we just contract 10 nodes together. So that's fine, yeah. But like the degree will be like around 10 R, maybe not exactly 10 R, because when you contract 10 nodes together, there can be some edges inside here, right? So, but that's fine. But okay, we can actually, okay, that's kind of cheating, but I want to just tell you that there is a way to really just modify the cut matching game a bit so that it really fit into our purpose. So by which I mean that consider the following, where think like, okay, so let's say this is degree profile D here, and D is in this, okay. And now, what if the game is like this? The game for the cut matching is that from the beginning, suppose that in each round, okay, now each node have its demand, right? V have its own demand, dV. We want that at the end, the degree of V is like some multiple of R times something. Yeah. Okay. Now, what if we define the cut matching game such that in each round, you divide the graph into two sides, such that the total demand on the A side is the same thing as the total demand on the B side. And now instead of saying that we want to find, like we can, like let's say that we ask a matching player to return not a matching, but a B matching. Yeah. So that is like we kind of really modify the game so that it fits our purpose. So asks the matching player to return a B matching. So what is B matching? So B matching is that like it's really like this. That is, it's a matching such. It's like a graph such that when each node when node V have demand dV, then like this, there are like basically dV edges incident to it. Yeah. So it's just a subgraph such that like it's a bipartite graph such that the degree like you can specify the degree of each node and the degree like it's a subgraph. Yeah. H is like is a, let's say, D matching if degree of each node is D, dV. Yeah. And H is bipartite. Okay. Yeah. So if we be more flexible, like if suppose that we can ask something more from a matching player to not just return some matching, but you can specify this demand to them, but ask for the like this D matching, then we can actually make sure that in each round the degree of each node is increased by this dV, and so at the end the degree of every node will be like like R times dV, something that we want. Yeah. So okay. Okay. So the next thing is that what if okay. What if we say that the matching player is a bit more flexible, but so if we allow the matching player to return a fractional matching between A and B. So let me define a fractional matching. Well, so what I mean is just that fractional matching is very similar to matching. It's just that now it's not the case that each node has one edge incident to it. It's just that you can have a lot of edges here, and each of the edge now has fractional value on it. So like 0.1, 0.2, and so on. But the sum of this is at most 1. So, okay, just to be more precise, basically, at most 1, yeah. right? Yeah. Okay. Right.
We'll assume that each vertex on the left is natural.
Say again.
We will assume equal to 1 for our cut matching.
Sorry, I don't hear.
We have fractional matching, it should be less than equal to 1, but for cut matching game, we want the AIs to be.
Right. Yeah. Yeah. For the in the cut matching game, basically, we want the size of this fractional matching to be of size A, which means that if the cut player chooses A, then there is no choice for the matching player. Even if we allow at most 1, every node here will be fractionally matched. But each of them, the sum here will be exactly 1, actually. Yeah. Yeah, thanks. Okay. Good. So now, I want to say that, okay, suppose that we really just do this, like just look at the same process, but except that now in each round, the matching player return this fractional matching. All right. So, and we repeat this process. So what we will get at the end is not, is now a weighted graph, right? If we just say that, okay, what if here it returns fractional matching? And we do everything in the same way. Yeah. At the end, we will get some weighted graph such that, and let's say we choose a cut play. The cut player is also choose a bisection, not just a cut too. Then what we will get is a weighted graph where every node has weighted degree R. Right? It's a uniform degree weighted graph still. Yeah. And my claim is that this graph still, so get weighted graph. And the claim is that this weighted graph will still be an expander, actually. That is, you will have that for all S. Then the weight of edges crossing S is, if you compare it to the size of S, this is still going to be large. After I last, which is maybe log n round or log square, or so you will still have that the weighted expansion is still big. Yeah. And now I just want to argue why this is the case. Okay. And there are like 2 ways to look at this. One is just try to really follow the proof and see that, like, try to adjust the proof accordingly. And a way to adjust the proof is that we can look at our goal, right? Here we said that we look, the strategy of our proof before is that we just, we analyze this random walk process, yeah, where we said that, okay, look at this random walk process, and then when you add a matching in each round, you can define how you do a random walk step. And if at the end, this random walk step is such that after log square round, every node can reach any other node in the uniform way, then you're done. Now we can try to just now say that, okay, in each round it's not a matching anymore. It's a fractional matching. But there is a very natural way for you to actually define this process for fractional matching. And the way is that, okay, instead of saying that with probability half, you stay at the same place, and with probability half, you just go to another node that you match. Now, you say that, okay, still here, the same here. With probability half, you stay at the same place. But now, in each round, you have, like, let's say, you have, let's say, yeah, this is, maybe this is, how much? Yeah. Then you just said that with probability, here with probability half, you will jump to other node proportion to the proportion to your fractional matching edge incident to you, right? So, like either you stay at the same place with probability half, or you jump to other node in the way that proportion to this weight. Yeah. Is this process clear? Okay. Good. And then you will be able to like just follow the same thing. You will be able to show that after log n round or log square, you will get something like this. Yeah. So like my point is that this framework of cut matching game is quite flexible. We really talk about integral matching in the work in class, but and we get uniform degree graph, but you can make the expander have degree as much, like in any degree profile that you want, and also fractional matching also is fine. But let me tell you a bit more about fractional matching. Like, there is like a very good intuition why it should just work actually, and the reason is that so any fractional matching is just a convex combination of integral matching. And now you can think of, okay, now in each round, like if the matching player gives you a fractional matching instead of an integral matching, it means that he actually gives you a bunch of matching, and you can randomly choose which of the integral matching you follow. So it's like the random process should even mix more rapidly. Is this intuition, does it make sense to you? Yeah. So in this sense, fractional matching is actually better for you. To say that after some rounds, then the random walk mix. Yeah. Okay. Okay. So we just defined the random walk process, but the thing is just that the algorithm for the cut player actually basically you don't need to change anything. Yeah, you just really just define it in the same way for the deterministic. For the deterministic algorithm, what you do is now that the graph is a weighted graph in each round, you just find a balanced sparse cut, but with respect to this weighted graph, right? And for the randomized algorithm, okay, maybe I should tell you a bit. For the randomized algorithm, we said that what in each round, what we do is just to choose a random vector R, multiply this with this sequence of matrix M1 up to Mi-1, where each of the M is defined based on the matching. Now, if the matching is now fractional, well, you will basically need to define Mi in the analogous way for the fractional matching. So how would we define that? Then, well, it's gonna be like really like this. That is, like for each edge. For each matching edge A and B with, let's say, 0.1 here, well, then you will you just add like 0.1 over 2, 0.1 over 2. Like for each fractional matching edge, you just add 4 non-zero entry into this matrix. You can verify that this is the one that really like if you define it like this, then you get this equality. But once you define it like this, you can see that the number of non-zero entry in this matrix M is just proportion to the number of edges in the fractional matching, like 4 times or 2 times the number of edges in the fractional matching. So the running time to compute this thing here is maybe not O(n) anymore, just because there can be more than n edges in the fractional matching, but the running time is still proportional to the number of edges in the fractional matching. So a time will be like maybe times I, yeah. Right. Okay. Question about this? Okay. Second, chip, chip, chip. So it turns out that so this is about some related project to card matching game. So, by the way, how many of you have heard about multiplicative weight update or have seen it before? You, not, not yet for you too, right? So I think I will cover it in class too, but it is just some like very powerful, very natural algorithm to do something, like to do a lot of things. And now it turns out that I think in this paper, they kind of show, so okay, very roughly speaking, multiplicative weight update is like some iterative process, like think of gradient descent or something like that, some iterative process that kind of converge your solution to something good for some optimization problem. Yeah. So, and there is a matrix version of it, but anyway, it is related to, like, it's just special case of something called mirror descent. Yeah. So mirror descent is like a very generic way to optimize something. One special case of mirror descent is just gradient descent. Now one special case of mirror descent is matrix weight update. Yeah. So it's like very generic optimization algorithm. And so it's very cool. Now, so I never, like, I don't know much about this, but it turns out that, like, in this paper, they show that a card matching game actually can be seen as this weight update frame, like can be seen as matrix multiplicative weight update. So it would be nice if one can try to understand this paper. And so what I know is that this connection, even in this paper, is not super explicit. But once you really read this paper, maybe by really understanding it, then try to explicitly explain the connection between these two things would be cool. Yeah. Because both of the things are cool stuff. Trying to see connection is good. Yeah. All right. So yeah, I don't have much from here. So yeah, I think I'm done. Is there something you wanna ask or discuss? Otherwise, we will just finish. All right, then yeah, see you next time.
I just wanted to know other the two triggers over all accounts. That good enough.
It's a polymer time.
Yeah, but it was offline.
Let's talk about that.
Okay.
Yeah, interesting. Because if you want to list all the cut, like listing all the cut trivially, like there are just too many cuts, right? N to the C cut.
Yeah.
But you said that you will list not all the cuts, but somehow still in polymer time. Let's talk about it. Yeah.